Let's look at proposition number 33 of book 3 of Euclid's Elements. The proposition says, given a line segment AB and an angle PCQ, we have to construct a circular segment such that the segment contains or has this angle. How do we go about doing this? First thing that we will do is copy this angle to A. We know how to do that. Circle, circle, intersect, and we join AD. So now this angle is equal to PCQ. So DAB is equal to PCQ. Okay, now let me hide these circles. What do you think is the next step? What we are going to do is we are going to draw a line perpendicular to AD. Again, we know this how to do. Circle, intersect, circle, and the line joining the intersections K1, K2. Okay, so again, let's get rid of this. So we have this perpendicular to AD. I'm sure you are able to guess where we are going. I will bisect AB. So circle, line crossing the intersects of these two circles. And the intersection point F. F is the midpoint of AB. So let's get rid of this. Now what is the next step? Oh, we got rid of the perpendicular line as well. We need that. Okay, now if you notice, this perpendicular to AD is also intersecting with the bisecting line of AB. So let's mark this point of intersection as G, and let's join BG, and let's remove these lines. Very distracting. There is one more line, and now let's join these points FG, and okay, I need one more thing. Now what we are going to do is, keeping G as the center and AG or BG as the radius, we'll draw a circle, and let's mark the intersection of the circle with this line as E. And now let's get rid of this line, and let's join these points. And here we have constructed a circle. Of course, what the proposition talks of is the segment of the circle. So that segment of the circle is ABE, which has an angle AEB, which is going to be equal to angle DAE. Remember, angles in alternate segments. So here DA is a tangent. This is perpendicular to the tangent, and AB is a line which is cutting this circle through the point of contact of the tangent. So these angles in the alternate segments will be equal. So AEB is equal to DAB, which is in turn equal to PC. So we have constructed the circular segment or segment of a circle which contains the given angle. Now let's look at the second case, because this angle can be an acute angle, it can be a right angle, or it can be an obtuse angle. We have already looked at the case of acute angle. So now let's look at right angle. So we have to construct a segment which contains an angle equal to a right angle. Again, we draw a line passing through A by making sure that it forms an angle equal to angle PCQ, which is a right angle. We know how to do that. Circle, intersect, circle, and the point of intersection. And let's join AD. We are going to bisect AB. So again, we know how to do that. Circle, bisecting line, the point of intersection. Again, we can get rid of all these. So this is the midpoint. And now what we do is, keeping the center at F, we draw a circle of radius AF or BF. Now remember, we have to have an angle in the segment. So let's take a random point on the circular segment. It doesn't matter where this is. And let's join AE and let's join PE. Then you will notice that angle PCQ has been copied here at A, and this is an angle which is on a semicircle. So angle on a semicircle is always right angle. So this is equal to this is equal to this. That means angle AEB is equal to PCQ. So we have constructed a circular segment AEB, which contains an angle equal to PCQ, or a given angle. Now let's look at the case where the given angle is an obtuse angle. So let's see how we can construct a circular segment which contains an angle which is equal to this obtuse angle. So again, we draw a line at A which will form an angle equal to PCQ on AB. So we know how to do that. So I'll just keep making these visible, right? And we draw a line. And now we can get rid of these. So now this angle BAD is equal to PC. Now let's draw a line perpendicular to this line at A, perpendicular to AD. Now let's bisect this, or in other words, let's mark the midpoint of AB. Since we know, I'm directly marking it. And at F, let's draw a line perpendicular to AB. And let's mark the intersection of these two lines as G. Let's join BG. Let's join FG and AG so that I can get rid of those lines. Now, keeping the center at G, let's draw a circle of radius AG. Now, which circular segment contains this angle? So again, we take a random point on the circle on this side, and let's join BH and AH. We know angle BAD is equal to PCQ, and we know that angle AHB, or rather BHA, would be equal to BAD. Why? Again, remember, this is an angle in this circular segment, and this is an angle in this circular segment. So these are alternate segments. So angles in alternate segments are equal to each other. And this angle is equal to this angle because we copied it. So therefore, angle BHA is equal to PCQ. So we have formed a circular segment AHB, which contains an angle which is equal to the given angle. Okay, now remember, when we are trying to prove this, we can't just say G is the center, and if we draw a circle of radius AG, that circle will pass through B. So we have to prove that AG equal to B. But that's not a very complicated thing, because these two triangles will be congruent. Why? Because F bisects AB. So that means AF equal to BF. FG is common. And this is a bisecting line, so which means these two angles are equal. So side angle side, these two triangles are congruent. And since these two triangles are congruent, we can say AG equal to BG, which means that if we take the center as G and AG as the radius, the circle drawn will pass through P. So when you're proving it, you have to be a little bit more rigorous. So that is proposition 33 of book 3 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download, refer to it, and if you feel somebody else can benefit from it, please do share it. That's it for now. Bye.